Hello, my name is Andrew Takis and I'm going to be solving number 1 on group project number 3. So what this problem is going to be asking is, first we need to be finding what tan x minus x over x to the power of 3 is going to be when we find the limit as x approaches 0. And the problem asks us to do this using L'Hospital's rule, and we're going to be using it 3 times here. And then on the second part of the question, it's going to be asking, well, look, find the power series of tan x and use that power series of tan x to evaluate the limit as x approaches 0. So to first start on the first part, what we would say is, well, look, L'Hospital's rule is going to be the limit of x is going to be approaching a constant of f of x over g of x. This is going to be the same thing as saying limit of x approaching this constant of f prime of x over g of x. And we can just keep on finding the derivative here. So what we do is first we find the derivative of tan x minus x, which we know is going to be derivative of tan x minus derivative of x. Derivative of tan x is going to be secant squared x, and derivative of x is just going to be equal to 1. So we know in the numerator we have secant squared x minus 1, which is a trigonometric identity, which we can say is equal to tan squared x. And then in the denominator, what we're going to have is we're going to be having the derivative of x to the power of 3. This is really simple derivative. What we have to do is just drop down using the little quick derivative tools we have and say this is equal to 3x squared. So that's how we get the first derivative. Then to get the second derivative, we have to start using the chain rule. So we're finding derivative of tan squared x in the numerator. This is going to be the same thing as saying derivative of g squared, differentiating for g, times tan, differentiating for g, and then we're going to be finding the derivative of tan x and with respect to x. So we know derivative of g squared is going to be 2g, and then like we did earlier, derivative of tan x is just going to be secant squared x. So we can say this is going to be equal to, well, plugging back in for g, 2 times tan x times secant squared x. And then what we can say is, well, look, what is tangent? Tangent is sine over cosine. So we have 2 sine x over cosine x, and then we're going to be multiplying by secant squared x, which is the same thing as saying, well, secant is 1 over cosine, but we have secant squared, so we have 1 squared over cosine squared. So what this gets us is 2 sine x over cosine to the power of 3x. And then in the denominator, what we do here is, well, we have derivative of 3x squared is equal to 6x. And what we do here is, well, we can simplify what we have in the denominator, 6x, in the numerator we have a 2. We can simplify this, and we can say, well, 2 sine x over 6x minus cosine to the power of 3x is going to be the same thing as saying sine x over 3 times x times cosine to the power of 3x. So we have to differentiate one more time using L'Hospital's rule. So what we're differentiating now is 3x times cosine to the power of 3x is, and we know this is going to be equal to, well, this is going to be a little bit more complicated. We can use a differentiating rule to say the derivative of 3x times cosine to the power of 3x plus 3x times the derivative of cosine to the power of 3x is going to be equal to that derivative. So that's going to be equal to, well, derivative of 3x is just going to be 3. And then we're just going to be multiplying that by cosine to the power of 3. So we know the first part is going to be 3 times cosine to the power of 3x. And then for the second part, what we're going to be adding it to, 3x times derivative of cosine to the power of 3x. And I said derivative of cosine to the power of 3x is going to be equal to, well, we have this right here. This is a little differentiating tactic that you can use to solve this derivative of cosine. And what we do here is, because these will cancel out, because we know d of cosine to the power of 3x over d times cosine to the power of x times derivative of cosine of x over dx. This denominator and this numerator cancel out, so what we ultimately have is going to be d of x of cosine to the power of 3x, which is just derivative of cosine to the power of 3x. So solving for this, what we ultimately get is 3 cosine to the power of 3x plus 3 times, and then now we have cosine squared x times negative sine x. And what we can do is, well, look, we're finding the limit for all of this. That was our denominator, and we got our numerator earlier, which was just sine x. Or it was just cosine x. So what we do here is we find the limit as x approaches 0, and we have cosine x over, and then here's our denominator. What I first do is I cancel out the cosines by taking one out of the 3 cosine to the power of 3x. And then what I do after that is I just plug in 0 to evaluate the limit. So we have 1 over 3 times 1 minus 9 times 0 times 1 times 0. We ultimately just get 1 over 3. This was a little bit of work to find the derivative, to find this limit using L'Hospital's rule. So now we can do it using the power series of tan x. So what I do is I use the Maclaurin series of tan x, which is a power series which is just centered at 0. And we know the Maclaurin series of tan x is going to be equal to, well, x plus x to the power of 3 over 3 plus 2x to the power of 5 over 15 plus 17x to the power of 7 over 315. And this can go on and on and on. It's just the expansion, and this goes on for infinity. So we only need to use these first 4 terms right here to solve. So what we do from here is, well, we have our equation, we have what we're trying to find, but instead of tan x, we plug in what we know the expansion is, which is x plus x to the power of 3 over 3 plus 2x to the power of 5 over 15, and on and on and on. But we can see here, we have an x at the front, a positive x, and then a minus x. So these x's cancel out. So now we have everything from here, and then this is all going to be divided by x to the power of 3. So we can say, look, here's the limit, and I dropped it, so I just made it, I made it so that it's all being divided by x to the power of 3. So now we have the limit of x approaching 0 of x to the power of 3 over 3 times x to the power of 3, and then now we're adding that to 2x to the power of 5 over 15 times x to the power of 3, and we're going to be adding that to 17x to the power of 7 over 315 times x to the power of 3. And this is going to go on for infinity. So what we can say is, well, look, this is a really easy limit to evaluate. The limit of x approaching 0 of x to the power of 3 over 3 times x to the power of 3. And these x to the power of 3's just cancel out, so we're just finding the limit of x approaching 0 of 1 over 3. For here we have the limit of x approaching 0 of 2 of x to the power of 5 over 15 times x to the power of 3. And then we're going to be adding that to the limit of x approaching 0 of 17 times x to the power of 7 over 315 times x to the power of 3. And this would go on for infinity, but like I said, we only need these first couple of terms to understand what's happening here. So I'm able to drop down and find the limit of everything just because it's a limit rule. It's the same thing as saying if you have the limit of 2 plus x, it's the same thing as saying the limit of 2 plus the limit of x. So that's just basically how I went from here to there. And then from then on, well, I just evaluate limit of x approaching 0 of 1 over 3. That's just going to be equal to 1 over 3. And then here we can simplify, well, we have x to the power of 3 on the denominator, x to the power of 5 on the numerator. That's just x to the power of 2. And then we plug in for x is approaching 0, so we can just plug in 0. And we can see this whole thing is going to be equal to 0. And the same thing for the next number. And this would continue on and on forever. Because as we see, the power that x is being raised of is going to increase. So x to the power of 5 is going to be x to the power of 7, x to the power of 9. It's just going to further increase that power. And then in the denominator, it's always going to say x to the power of 3, which we got earlier in our equation. So we know that everything coming on is just going to be equal to 0 because the coefficients won't matter and all the x's are approaching 0, so that it's just going to be all equal to 0. So we add these all up. We have 1 over 3 plus 0 plus 0 plus 0, and it would be an infinite sequence of zeros, so we just know it's equal to 1 over 3. And this was a little bit of a faster way to solve this initial equation rather than like a brute force way using like the L'Hospital's rule. And yeah, that's how you solve problem number 1 for group project number 3. Thank you.